think we're live. All right, so we took a few days off, 4th of July weekend and everything. We're back continuing our beams in bending. So these are beams that are flexing one way or another. We have done a couple of things with these beams. We've looked at how to go in and draw a free body diagram, splitting the beam open to see what internal shear force and internal bending moment are inside the beam at whatever location. So I think we're back now. All right, sorry about that. Now we are starting. Last time we did the shear set of rules. So remember, if we let me pull those up so we can look at them. So last time let's see here. We drew this free body diagram. We put every imaginable load that we could think of, point load, concentrated moment, and some kind of distributed load onto a single spot in a beam. And then we looked at that spot as a very thin sliver, delta X thick. And we were looking first at just the summation of forces in the Y direction, so the shear forces. And we developed an equation here, this yellow one, that went in and showed us the generic equation for delta V, so change in shear. And we set up a couple of rules, and we drew a shear diagram for a beam that has some point loads on it and a distributed load. Doesn't have a concentrated moment. It did have a roller here and a pin over at the right end of the beam. And so that's where we left off at. We ran out of time to do the next part after that. I think what I want to do to get back in the swing of doing this stuff is let's look at a web work problem that does the slice a beam open and figure out the equation for shear and bending moment at that point. So that's kind of going back 2 lectures, I think. But I have some of those pulled up here. Is this one? Yes. So interval. So we've got a beam. Why don't we work through some of this? I don't know if we'll work through all of it, but some of this just to get back into what we were doing. And then we will finish up all of the background information for shear and bending diagrams. And then tomorrow, we will do examples of shear and bending diagrams. Let's see what else we have for tomorrow. Tomorrow's the 8th. Moments of inertia, lab 1. We may move those a little bit. And do shear and bending examples on the 8th and move, well, there's already moments of inertia on the 12th, so we might just move that a little bit. All right, we'll worry about that later. So I've got my example here that I'm going to work on. This beam looks like some kind of I-beam. It doesn't really matter for what we're doing here because we're not doing anything related to the stress in the beam. We're just doing the equations of the shear and bending moment in these different sections of the beam. So we don't actually need to know anything about the beam in particular to do that. Why don't we work on finding our reactions first? So we'll figure out we have a roller here at D. So we're going to replace this with that. We've got a pin at B. This setup doesn't have any forces that are in the X direction or have an X component, so even though there's a pin here, I really only have a vertical reaction. I don't have a horizontal reaction at the pin. The concentrated moment, M, doesn't create any sort of X or Y force. All right, so let's put some things in here. 23 10 for F1. F2 is 1940. M is, wow, it's a big number. 15090. These units were pounds on these forces and foot-pounds on the concentrated moment. W is 1130 pounds per foot. We've got some dimensions. A is 7.6 feet, B 17.8, and C 5.7. Okay. So we've got all of our different units and dimensions and everything that we need. This problem, since we're doing these intervals, they have x listed as in the interval, or defining the interval location. So we do have to note that x is 0 way over here. You can see the y-axis showing me where x equals 0. So the very far left of the beam is x equals 0. Let's see if we can get these reactions at B and D. So to do that, usually the best thing is going to do a summation of moments at one of these points. In this case, let's do at B. It doesn't really matter, but that's the first one I looked at, so we'll do B. Let me make sure the chat is open here in case we have anything. It was covered up. All right. At B, we're going to need our calculator. We've got the F1, which is creating counterclockwise, so negative, according to my equation, 2310 times 7.6. I'm going to leave the units off just to try and save some space. Everything looks like it's in pounds and feet, so we don't have any mixed units of any sort. We've got the moment at B, so it's just plus or minus. In this case, it's plus because it matches the direction I said was positive. 15,090. The distributed load is 1,030 pounds per foot, and it is spread over 17.8 feet. So it has a total, I'll make it in green, of 20,114 pounds. And it would go clockwise. 20,114 pounds. It has a moment arm of half of B, basically. So B for me is 17.8 divided by 2, 8.9 feet. F2 is an additional point load that we need to take into account. Looks like I'm going to have to move this equation to get some room. Let's put it up here. So F2 is positive clockwise moment times B, 17.8 feet, minus this last one. I didn't label these. I've got this as RB and RD apparently, just looking at the problem statement down here. So minus RD times B plus C, so 17.8 plus 5.7, 23.5. And those have to add to 0, or else the beam is rotating about B, which it doesn't appear to be doing. So 2310 times 7.6, that's a negative one, plus 15,090 plus 20,114 times 8.9 plus 1940 times 17.8. Move RD to the other side, it becomes positive. So I just divide by 23.5. RD, the reaction at D, should be 8982.15. And then we can do summation of forces in Y equals 0 to get RB equal to, I don't know, let's just add it up real quick. So 2310. The moment doesn't go in there, so we leave that one out. 20,114, 1940 minus 8982.15 says it's 15,000. Oh, 15,000. 381.85. These are all pounds. Let's check our web work, see if we're anywhere near right. Let's see, what were our numbers. RB, I had 15381.85. I guess I have to put, yes, include units, so pounds. And D, I had 8982.15 pounds. Let's see. Yeah, it's both correct. All right. So that's the relatively straightforward part. On an exam, there might be an instance where you have to solve for the reactions, but probably not. They'll probably be given. I can't say with certainty that they will be or not, but that's not really part of the content we're learning right now. That's just something you need to be able to do to get to the content. So here's the content for this one. Filling in these blanks. So these blanks are where we want to go to specific intervals in the beam, cut it open in the center of that interval, and figure out what the shear force and bending moment are in that interval. So the first interval, 0 to 7.6 feet, that's this interval right here. I don't know if that shows up very well, but kind of does. It's the first, from A to B is what it is. So let's cut that thing open, draw our little free body diagram showing that, and on this we have 2310 shear M and X. X starts at the very left of this section. So it looks like it doesn't matter at all for summation of forces in the y direction equals 0. Negative 2310 minus v equals 0. So v equals negative 2310 anywhere in the section. That's what it looks like. If we do, make a point right here on the cut surface of our free body diagram and do moments about that point. I've got V does not create a moment. M is counterclockwise. I said clockwise is positive when I wrote the equation down, so that means it is minus M. And then minus 2310 with a moment arm of X equals 0. Move these to the other side, or let's move M to the other side so it's positive. So M of X equals negative 2310 times X. It does say to omit units from these equations we're going to put in. So let's see, negative 2310. I don't know if it's going to care if it's positive or negative, but we'll see. And 2310 times X. Another two correct ones. All right. That one was a relatively straightforward interval. On an exam 2 is where this would show up. On this exam 2, you wouldn't necessarily need to write out the equation for one of these like we're doing here. Like the answer wouldn't necessarily be the equation, but there will be some problems that are set up to where this is the better process. So I could envision this problem or this beam, and maybe you already know B and D, maybe you don't, I don't know the reactions at B and D, maybe not, depending on how hard the problem's supposed to be. But the question could be, given this beam, what is the bending moment at a point 10 feet from the left end? So that's exactly what we're doing here, except that instead of randomly picking a spot, if I said 10 feet from the left end, you go to the left end and you cut this thing off at 10 feet, do the exact same thing where you draw the free body diagram and write the summation of moments about that cut surface, and instead of getting a variable, x is not x is 10. So you put in a number for x and solve the equation to get the actual value for the bending moment 10 feet from the left end of the beam. So there will certainly be at least one problem set up where this is the preferred way to solve it, versus drawing the entire shear and bending diagram just to figure out that one point. Okay, let's do our interval 2, which should be from B to C. So here, I've already got a little line drawn there, so let's use that line. Okay, we have the same 2310. We have reaction at B, which we found to be 89. No, it was the bigger one. 1530. 381.85 pounds. Don't be confused. Remember, we drew the concentrated load representation of the distributed load. That's not actually there. It's just how we are, when we went to write this equation, where did it go? Right here. That's just how we put the distributed load in the moment equation to solve for the reactions. So that's why I draw it in a different color. I drew it in green, is so that it wouldn't be confused with an actual load that are all in red. We do have M here, which is 15,090 foot-pounds. We also have our distributed load that starts here and then gets ended. 1130 pounds per foot. And we have X also measured all the way from the left again out to here. That's X. Okay. Oh, and what we're looking for, we have the shear and bending moment. Remember, you do have to use these directions for the arrows if you were drawing them on the right end of a beam that you've cut open. If you're drawing them on the left end, you'd use the opposite arrows. Usually I am going to draw the right side like we're doing here, but there might be a reason that you want to draw the other side of the beam, and in that case you flip these arrows where shear is pointing up, bending moment is clockwise. Alright, let's see if we can do this one, and then that'll probably get us back up to where we were on doing this, and we can go back to our shear and bending diagram stuff. Alright, so let's do the easy one first. Forces in Y, or easier. So negative 2310 plus 15,381.85 minus however much of this distributed load we have, which is 1130 pounds per foot times X minus A, which my A is 7.6 feet. Now, I didn't put units on any of this, but hopefully you can keep track of what they are. Minus V equals 0. Technically now V is a function of X, so we'll put V of X because there is an X in there. The concentrated moment, 15,090 foot-pounds, doesn't go in this equation. It's not an X or a Y, so we leave it out entirely. So let's move V to the other side so it's positive. So V of X equals, we've got some numbers we can just add together here. 15,381.85 minus 2310 is 13,071.85 minus 1130 times X minus 7.6. So you could work on this. I have seen a couple of people ask questions about problems like this one from WebWork where they had the right set of numbers, but they were in a different form. Maybe they expanded the parentheses differently or collected terms differently or whatever. But their answer was the same, but WebWork was marking it wrong. So if you get in one of those situations where you know you're doing the right thing, but WebWork just won't take it on this problem, send me an email and we'll see if it's just something like that. In fact, it may do it for me right in here. So let's see. 13,071.85. No units on these, it said. Minus 1130 times X minus 7.6. Let's see if it's okay with that. It is. So, in fact, we have it in the exact same form that they have it in. So that probably helps. Okay, let's do the bending moment, since that's what we're about to do. We've actually already derived the if-then rules for the shear diagram, drawing it. But we need to do the bending moment ones. Summation of moments about our cut surface equals 0. Clockwise moments are going to be positive. All right. So I've got, I usually do these starting at the left end of the beam and working towards our right side. So let's do the negative 2310 times x, it's the first moment, plus 381.85, that's pounds right there, it's kind of hard to read, times, this one has a moment arm of x minus 7.6, this distance here, 7.6 feet. We could go ahead and put the concentrated moment in, just plus m, which is 15,090 foot-pounds, already in the right units. We've got to create a little lumped version of this guy so that we can take care of the distributed load without using calculus. So it's going to go counterclockwise. So minus the magnitude, the green arrow's magnitude, is 1,130 feet, or pounds per foot, times x minus 7.6 feet, times the moment arm of that distance, which is x minus 7.6 feet over 2, minus m, because it's drawn counterclockwise, and I said clockwise was positive. So equals 0. This is technically moment as a function of x, because there's several x's in here. Okay, let's see if we can simplify it a little bit. We could maybe put it in just like this and it would work out, but let's move m to the other side. So m of x becomes positive, and it equals, let's put a positive number up front. So 1590. Let's see, we've got minus, if we do these two, we'll have another number that we can add to that 1590. So 381.85 times 7.6. Wow, that's a giant number. 15. All right. Minus 116,902.06. Now we've got a couple of x. Oh no, there's another one. 1130 times 7.6. So that's another minus 8588. Oh, and there's another one of those right there, isn't it? I might leave those together. I think those are actually, instead of, since those are both x minus 7.6, I think I'm going to leave that together. In fact, I might need to do that with this. I think that's going to be easier if we leave those together as far as web work goes. So in fact, let's leave those together. I think that's going to be better in the long run. So now let's just do our minus 2310 times x plus 15,381.85 times x minus 7.6 minus 1130 divided by 2, 565 times x minus 7.6 squared. All right, does that take care of everything? I think it does. Let's try putting that into web work and see if it cares for that or not. Why don't we move that up so we can see it all at once. All right, so that's 1590 minus 2310. Let's do times x. I don't know how well it deals with the implied multiplication or not. Although it does fine with parentheses, so it would probably be okay. Oh, wait, need to close parentheses. Let's see if we got anywhere near the right thing. No, but let's see what we actually ended up with. Oh, I think I have a negative sign backwards somewhere, because they have a plus on that. Let's see. Oh, yeah, it is a plus. That's this term, so that should be a plus. Easy to get lost in our stuff here, particularly when we're going in a hurry. Now we're right. All right. So that maybe not to, quite this level, you know, I don't know if this level would be the thing. Although if I said x is 10 feet and you got this beam, then this is exactly the equation you would need to develop, except x is 10, and you then, instead of an equation, you get an actual number out for the bending moment. So it is possible that you would have to do something along these lines. I would think more, you know, more like this. Well, this version over here, where it's a little simple equation. But it does depend on if this is one of the harder problems on the exam or kind of the middle of the road problem. All right. With all of that, let's get back to what we were doing before. So we had this. We need to copy this thing and carry it over to our new page, if it'll let me do that. So we're going to copy that and go to our new page that we were just on, somewhere down here. Okay, it did. And work on this one to write the summation of moments about the center point of it. And we're going to get a set of rules that will describe how we draw the bending moment diagram. So we already have the set of rules for drawing the shear diagram. We'll have to look at those again to refresh what they were, but we have those. And we need a similar set of rules for drawing the bending moment diagram. Most of the time when you're doing these beam analysis problems, the more important one is the bending moment diagram. The shear diagram can be important, but a lot of times it is important because it helps you get the bending moment diagram. Most of these times the beams are not going to fail in a direct shear type of failure. It is possible, but it's usually not the mode of failure that happens. All right. So let's do summation of moments. We're going to do, let's call this, I don't know, A. About A equals 0. I'll use clockwise positive, although it doesn't matter, you know, where I'm writing the equation, it doesn't matter. These directions do matter because they are set up so that we have tension on the bottom of the beam when we have a positive moment applied to it, positive internal bending moment. So maybe not applied to it, but inside it. All right, let's see. Let's do the same type of trick we did here and say that moment on the right-hand side is just equal to the moment on the left-hand side plus any change in moment. So however much it changed from one point to the other, that's how we're going to define it. So instead of writing mr into our equation, we can write ml plus delta m to represent the moment on the right-hand side. All right, let's do those. So we've got, say clockwise is positive, so m plus ml minus mr, which is ml plus delta m. And there's that ml minus ml that we want to cancel out, so that's good. P does not create a moment about point A, it's applied right to it. The distributed load is a little trickier. Now it's really easy the way I drew it. The way I drew it, you kind of have two halves of this distributed load, and it's obvious that, you know, this and this would just cancel each other out. So you wouldn't have to worry about it. But what if you had some, you know, strange shape distributed load? So if you have some strange shape, it still works the same way, but the strange one would be some kind of function of x, so some coefficient, whatever it is, that describes the shape of this distributed load, times w. And we could deal with that too. You know, some of it's going to be on the left-hand side of point A, some of it's going to be on the right-hand side of point A. And it's defined by this function a of x times the magnitude of the distributed load, the pounds per foot. So either way you want to think about it, it will cancel itself out. When we do the same type of thing we did last time, and we make delta x very small, then x is getting very small also. And so this term essentially becomes a flat line that cancels out on either side. So it may not exactly cancel out, but the effect of it is small compared to all the other things we're looking at when you look at very narrow slices of it. So the distributed loads don't have the same effect when you look at narrow slices compared to these other things that are going on as far as the internal bending moment goes. So what I like to do is just make it simpler on my brain and think of it as, well, what if it's just an evenly distributed load? And well, let's leave those on there. And there I can look at it and say, well, this part basically cancels out this part because one of them creates a clockwise moment, the other one creates a counterclockwise moment, and they're both the same moment and they cancel each other out. So that's the easier way for me to look at it and think of it, even though it still works when they don't cancel each other out. All right, the other thing we have to deal with is V. Now, I do have this, but I'm actually not going to use that. I'm going to use VR and VL, and we'll deal with them some other way. So VL is plus, so VL times delta x over 2 would be its moment arm. And VR also goes around clockwise. Notice their directions are such that they would both create clockwise moments. So plus VR times delta x over 2. Those are all the things that create moments about A. All right, so they equal 0. All right, so let's simplify this sum. First of all, I've got those that just go away, so that's easy. I've got M minus delta M plus, and then this guy I'm going to write in a way like this. So I've got this delta x over 2 that's common with both of them. And I could think of it as VL plus VR times, or let's do it the other way, I guess. Delta x over 2 equals 0. Let's go ahead and move delta m so it becomes positive. So delta m equals m plus this thing. If I look at that part, I kind of missed that part. I've got VL plus VR over 2 times delta x. That's another way to look at it. VL plus VR over 2 times delta x. When you take two numbers, VL and VR, you add them together and you divide by 2, all you did was you calculated an average. So delta M equals M plus some kind of average shear times delta x. And that is our equation that we can write our if-then statements about. Okay? So let's take that and if then. Okay? So if M equals 0. So this is actually most of the time. Like if we look at our beams, like there's only this one little spot where M does not equal 0. Most of the beam is M equals 0. So most of the time, this is what's happening in our shear diagram. M is just 0, and then we have delta M equals V times delta X. I want to drop the average off of there. It's just shear at that point. Because remember, delta X is getting really, really narrow, so it's just the shear at that point. So what this looks like is dm over dx equals V. So the slope of the bending moment diagram, so we'll just do M diagram, equals V. And V could be a function of X, I suppose, because it could change from one point to another. So what this means is when I'm drawing the bending moment diagram, I'm actually looking at the shear diagram. And if I want to figure out anything about the bending moment diagram, I really mainly look at the shear diagram and look at what's going on there. So let's go back and look at our shear diagram that we drew before here. Maybe let's copy this stuff because we're going to need it to... Okay. Let's just carry that to our new page. Put it down here. Okay. So we've got a lot of sections. Remember this area here and here. That little piece. That is the shear diagram. And so a lot of places the shear is constant. Like it's not 0 here, but it's just a constant. And so if I have a constant shear, then that means I have a constant slope in the moment diagram. And I can also tell, the keyboard is stuck under there. I can also tell that, well, in this section here, I have a negative constant shear. So that means that I have a negative slope, but it's constant. So just this straight line, but it's pointing downwards in my moment diagram in that interval of the beam. Here, I've got a positive shear, a constant shear, and it's positive. So the moment diagram is trying to go upwards. You know, it's got a constant slope, so a straight line, but not vertical, but not curved is what I'm trying to say. It's straight, not vertical though. In a straight upward facing because it's a positive shear line. This section, see if I can get rid of, why is it not erasing that? Well, I'd like for it to erase that line I drew, but it's not acting like it wants to. Guess maybe we're just stuck with it. All right, so we'll draw a different color. This section, I don't have a constant shear. It's positive, so the general trend of my moment diagram is upwards because I have positive shear here. Actually, at that point, I have 0 shear. So at that point, I have 0 shear, meaning the slope of the moment diagram is 0, so it's horizontal at that point. It's not that the moment equals 0, but the slope of the moment diagram is 0, which means it's reached a horizontal slope. So what I need to be able to do is take these different, the rectangular areas in my shear diagram are pretty easy. It's just a straight line up or down, you know, tilted up or down, sloping up or down. It's not a step change. So those are pretty straightforward because it is the shear positive or negative. But here, where it's this triangular shape, I've got a constantly changing shear. So that does mean it's a little bit different. It means my slope is constantly changing. So let's look at, there's 4 different categories that this could be in. Really don't know why it has lost the ability to undo stuff, but oh well. So let's draw our 4 different possibilities. So in my shear diagram, there are, just make some room. Oh, that didn't make room. Let's see, let's just do it this way. We may have to just repaste that when we're ready for it, but we'll leave it here for now. There's 4 different things that could be going on. So this line will be the shear equals 0 kind of baseline. So I could have a shear that's positive, but it is approaching 0. I could have a shear that's positive and getting more positive. I could have a shear that is negative and approaching 0 as we move to the right is what I'm talking about. And then I could have one that starts at 0 and as we move to the right gets more and more negative. Now, I could have other shapes too. I could have parabolas and all sorts of things, depending on the distributed load. Remember, the triangles in the shear are created by the distributed loads on the beam. And we've only dealt with evenly distributed loads. And in this course, that's all we'll deal with. It would work the same way, except that if I had an unevenly distributed load, like a triangle shaped load on the beam, then I'd have a parabola shaped shear, and it'd have a, an even more curvy type moment. This gets the same idea across though, but it's simpler to deal with. So if I have these shapes in the shear diagram, and the shear controls the slope of the moment diagram, so underneath these, when we draw this, so when we draw the bending moment, it's going to be down here. It's going to be down here somewhere. Hey, it's doing undo now. All right. So the bending moment diagram is going to look like this one. The shear is positive, so it's going to have a generally, positive slope. But it starts out as a high shear of some value and gets to 0. So it's going to start out with a high slope and go to 0. So it's going to have that kind of shape. Here, again, positive trend, except that it's getting more and more shear. So the shear is increasing, starting at 0 and increasing. So it's going to have this kind of shape. Here, these are below V equals 0. That's what this line is showing me. So here, they're negative. Well, why did I draw that line? I don't actually want that line on there. It's got a negative value. It starts out steep, so a large shear, and it goes to 0. So large slope that approaches 0. Again, this one's negative trend. But it gets more and more steep. So it starts out at horizontal and gets steeper and steeper. So those are the 4 different shapes that we might encounter in these shear and bending diagrams. Once you start drawing some of these, they'll make more sense as you get to doing that part. The other thing of this is the change. The height here is equal to, you can kind of see it right here, delta M equals V times delta X. So delta X doesn't always have to be a tiny little sliver. Delta X could just be X. It could be here for like this first area. This one, V is negative 2190, and delta X is this distance, 2.3 feet. So it's just the area of the thing. And so the change in moment from wherever you started to wherever you end up is equal to the area in that section of the shear diagram. And it could be a negative change like this first one. I've got a negative area or negative V times a positive X, but that has a negative area. It doesn't have an actual negative area, but it means that if I integrated the curve here, I would get a negative number. And that's what you're doing. For most of the bending moment diagram, you are integrating the shear diagram in order to figure out what M equals. So most of the time, that's what you're doing. Delta M equals V times delta X. Integrate both sides, you get M equals the integral of V delta X. So the bending moment is the integral of the shearing diagram. And there is that one other thing. So remember, all of that was predicated on there's not a concentrated bending moment there, but what if there is? So maybe we have one little line here. M does not equal 0 as delta X approaches 0. So we get narrower and narrower to the point where we're at exactly the point where the bending moment occurs. So it doesn't matter all the other things that are occurring there, but we're narrowing down on the point where the bending moment is. Then our equation, delta x goes to 0. Where's our equation? Here it is. Delta m equals m plus v times delta x, but delta x is going to 0, so delta m equals m. So what that means is that there is a step change in m, well, m diagram, and that step change is equal to magnitude, the magnitude of the concentrated moment at that point. So, for instance, where's our little picture? Right here, if we were drawing the moment diagram and we had gotten to that point, the moment diagram would suddenly go up. This is a clockwise moment, so clockwise external moments, external concentrated moments, clockwise are positive in this setup. So it would have a positive step change in our moment diagram of wherever we were, plus 15,090 foot-pounds. So let's go back down here and let's see if we can draw the bending moment. Actually, let's recopy this guy because it's gotten too kind of junky. It should still be copied. Yeah, there we go. All right. So let's draw. This one doesn't have any concentrated bending moments on the beam, so we won't get to that. We'll do one after this. We'll have time. So we'll do another one and we'll make sure it has a concentrated bending moment on it. All right, so first we need to extend our guidelines because we need some room to draw our bending moment diagram. Kind of missed that one. It didn't want to snap to that spot. It's fine. And then we'll put a baseline down here. And this will be m equals 0 foot-pounds. And I won't foot-pounds because my units are feet for my x dimensions and pounds for the forces. Okay. It looks like, let's just get a rough idea of what we're going to have. And usually the best way to do that is to actually break all of these shapes. In this case, I have triangles and rectangles, and do the area of each one. So the area of this guy is negative 2190 times 2.3, so 5,037 negative foot-pounds. This one is 3,042.5 times 2, 6,085. The triangle here, remember last time we had to figure out what its base was because the triangle didn't go the entire 5.1 feet. And we did that by recognizing that the slope of the triangle here is the value of the distributed load. So the distributed load points down, 700 pounds per foot. So the slope of this triangle, the hypotenuse of this triangle, is negative because it's pointing down, 750 pounds per foot. The height of the triangle started at 3,042.5. Divide that by the 750, and it says that x is 4.06 feet. So that's how long it took to get from 3,042.5 pounds down to 0 if I lose 750 pounds per foot. So it takes 4 feet to do that. So the area of this triangle has a height of 3042.5, a base of 4.06. It is a triangle, so don't forget to divide by 2. It's still positive. I'm running out of room to write things. We'll just erase that. 6176.3. I rounded a little bit there, so we'll have a little tiny error at the end. This tiny little triangle right here, I usually like to do the negative areas below here, but I'm kind of running out of room. It's going to get crowded, but we'll do it anyway. So that triangle has a height of 782.5, but it's negative, times a base of 1.04, divided by 2 to get the area, negative 406.9. And then this last one has a height of negative 2522.5 and a base of 2.7, so it has negative 6810.75. All right. So now I've got an idea. I'm going to go down 5,000, go up 6,000, so I'm at 1,000, go up another 6,000. I'm going to be up at around 7,000, then I'm going to drop back down. So let's see, 1, 2, 3, 4, 5, 6, 7. We can probably make that work. So these will each be 1,000. And now it's actually going to go start out by going down 1, 2, 3, 4, 5 down to negative 5,037. So here's how you draw these. You start at 0. Remember the shear diagram, you also start at 0. So we start at 0. And the shear diagram didn't change most of the time unless there was a distributed load or a point load. The moment diagram is based on the shear diagram. So basically the shear diagram kind of looks like a bunch of distributed loads to the moment diagram. So here I've got a negative constant slope. So I'm going to start at 0 and go down by the area of this first rectangle, 5,037. So I'm going to go down to here, negative 5,037, and the shear is constant in this area. So I've got a constantly negative 2190 is the value of the shear, 2,190 pounds. So it's constant, not changing. That means my slope here is not changing. So it's just a straight line. Then I have this weird, immediate shift to a positive. So over the next 2 feet, I gain, so let's put this in my calculator. I'm at negative 5,037 currently. I'm going to gain the area of this triangle. So plus 6085. I'm at 1,048. So right in here. This shear is constant. So that means the slope here is constant. So I do have a discontinuity, which is because this is where there was a support. So this V shape down here is because I had a roller right at this point that was creating a discontinuity in the shape. Normally you don't have this big of discontinuity, but you can. Now I still am positive. Oh, and you know what? I should go in and mark this as a reference point too, because that's the point where the shear goes from positive to negative in these triangles. So that I'm at 1,048. I'm going to add 6,176.3. So I'm adding the area of this positive part of the triangle. So that gets me to 7,224.3. Right? Let's say it's right there. Whoops. Get off of there. Right there. This one, however, is not a constant shear. The shear is started out at 3,000 and it goes to 0. So it ends up a horizontal, which I know is 0. So that means it ends up horizontal. And it started out pretty steep, And so I kind of connect the curve between there, something like that, to show that it's curved. It starts out steep, meaning that there's a high shear, ends up horizontal because there's zero shear. This tiny little triangle right here, I found the peak, so I could stop here, but it's usually good to go ahead and do the whole thing to see if you've done it correctly. So I'm at 7,224. I'm going to subtract off I'm going to subtract off 406.9. So right here, 6817.4. Start it horizontal because the shear is 0, and then get, kind of steeper. Probably not that dramatic, but that's what I've got to work with. And then the last box is, I'm at 6817.4. The area of the last box is 6810.75. So if I subtract those, 6810.75, I get 6.65. So essentially 0. Remember, I did say that I rounded, and then all of these have been rounded. All these areas have been rounded. So all that little bit of rounding, I should have ended up exactly at 0. But I'm okay with, my maximum being, max is 7,224.3 foot-pounds, and I'm off by 6 or 7 foot-pounds. I'm okay with that kind of difference. If this was off by 600, then that would probably be a problem. This is a straight line because the shear in this last section was constant. So now I've got a picture of the bending moment anywhere in this beam. And I've got the maximum located. And it's not a place I would have been able to locate just by looking at it either. Because it's not at any particular point, it's kind of in right here is where it occurs. So it's not at that point load, it's not at one of the supports or anything, it's not in the very middle, so it's kind of hard to identify that without a shear and bending diagram or writing out all the interval equations and figuring out where they peak at. So that is how we can go about finding shear and bending. You will have problems on the exam where instead of drawing an entire shear and bending diagram, because that's probably not going to be feasible in an exam, what you'll have is a beam, just the picture of the beam with the loads on it, and then you'll have options of different shapes for shear and bending diagrams, what they might look like. No magnitudes, just the shape of it. And based on knowing that, well, under the distributed load, I'm going to have a triangle shape for the shear and a curve for the moment, and figuring that out, you should be able to select the correct shape of the shear or bending, whichever it's asking for, based on things like that, without having to draw the whole thing. So I don't know that there might be a problem where the problem answer is not drawing the shear and bending diagram, but being able to draw the shear and bending diagram gets you towards the answer. So for instance, for this beam, the question could be, where is the maximum bending moment in this beam? And so you would have to figure out that, it is, and then let's see what it is. It is 2.3 plus 2 plus 4.06, 8.36 feet from the left end of the beam. And so that's the solution, is how far is it basically from, here to here? What's that distance? So that might be a way to solve, to ask one of these where you don't draw the picture itself. It's not the answer, but it tells you the answer by drawing it. All right, let's find one to work from scratch, and that should probably do it for today. So let me see. I had one, I thought. Oh no, that one doesn't have a bending moment on it. Let's find one that has a bending moment, so that we get to use one of theirs. Oh, that's got all kinds of stuff on it. So in web work, this is how you draw a shear and bending diagram in web work. You put the location of the different intervals, The shear force on the left and the right, is it a, what shape is it? Is it curved up or down, or, what? So not fun to do in multiple choice type settings, trying to draw this picture in a bunch of boxes. But that's the way WebWork works. All right, let's copy this guy. You know what? Let's not solve the reactions. Let's just look them up so that we save time on not doing that part. We've already done that plenty of times. So let's go find what RB and RE are supposed to equal. So they should be the first ones. 13, RB is first. Yes, RB is 13.35, whatever the kilonewtons. And RE is 15.02. All right, so I'm assuming that you could go in and get those values for the reactions just by doing moments about the pin and then forces in the Y. All right, let's take our, now that we have those, let's take our picture here. How do I want to? I actually don't know if it'll copy. Does it copy that kind of stuff? No, it plays the whole thing. Let's do it this way. Just get this. And paste it in there. And then let's put these guys. E is 15.02. B 13.35. And we need all our other values here. So M1, 17 kilonewton meters. Oh no, 1.7 kilonewton meters. W1, 2.9 kilonewtons per meter. I better put these so I don't mess them up. M2, 2.5 kilonewton meters. F, I don't see F. It's just not bold. 2.6 kilonewtons. W2, 5.1 kilonewtons per meter. We already have our reactions. A is 1.5 meters. B, 1.8. C, 2.3. And D, 1.9. All right. Let's get that at the top of our page. Let's draw our reference guidelines. So this A, this moment M1 kind of looks like it's the very end, but I've got A marked right here, so I'm going to put it at that line that I have marked. Let's get like that. Then we need one for this point. We need one here. We need one here, which they're snapping to the grid, but that's fine. We know what they represent. Let's do a horizontal one for where V equals 0. All right. So let's start drawing this thing. Let's draw it in blue. All right. So we start at 0. And we're going to need our calculator. I probably need to go ahead and lump these distributed loads. So 2.9 kilonewtons per meter times 1.5 meters. This guy is 4.35. I've got to divide this one into 2 because of that point load in the middle of it. So I have to do some of the distributed load, do the point load, the rest of the distributed load. So this is going to be 5.1 times 2.3. So this one's 11.73. And the other side of it is 5.1 times 1.9, 9.69 kilonewtons. Those are the lumped loads for those distributed loads. All right. So I've got an evenly distributed load. It's pointing down. I'm at 0. And the total magnitude of this distributed load when I lump it to one point is 4.35. So I go from 0 minus 4.35. So I'm down to negative 4.35. I'm going to make these count by 2's. And hopefully get enough room on here to do that. 2, 4, 6, 8, 10 will be up there. It'll work. It'll work. So it'll go down, what I say, 4.35. Okay. Then I have a point load, so plus 13.35. It's me to 9, 2, 4, 6, 8, 9. Then nothing, so just horizontal. Then minus, so I'm at 9, minus 11.73, so that's the first part of the distributed load. Gets me down to 2.7, so this is 2, 4, right in there, 2.73. Minus this point load of, I think that's 2.6, yeah, 2.6, so minus, oh, wait, hold on, that's negative. Negative 2.73. More like that. Minus 2.6 is, now this point load here is a step change. So I go straight down 2, 4, somewhere right there. Negative 5.33. Then I go down again, minus 9.69. So we're just going to go way down. In fact, I might just kind of chop it off right here and call it that, so because I don't want to draw it to scale, because it's actually negative 15.02. So it really should be much further down, but we're going to kind of chop it off. And then I have plus 1502, so that gets me back to 0. Now, just because you got the shear diagram to come out to 0 doesn't mean you automatically got it right. It's very easy to do the moment equation wrong, then do the y equation right when you're doing the reactions for the supports, and get this to start and end at 0 but still be wrong. So don't automatically assume that if you get to 0 you've done this right. If you get to 0 on the bending moment diagram, you're pretty much done it right. So I'm just kind of shading it in so I can keep track of what we've got here. All right, now let's do our areas. That's usually what I do next, is calculate the area of each one of these shapes in the shear diagram. So I've got negative 4.35 times a base of 1.5. It's a triangle, so divide by 2. So negative 3.26. Again, I'm having to round, so we won't end up exactly at 0. The next one has a height of positive 9 times 1.8, 16.2. This guy, we don't know the base of it, so we got to figure out the base. The height is 9. It has a slope of 5.1 kilonewtons per meter. I'm looking at it right here. So 9 divided by 5.1 is 1.76, which means this is 0.54, more or less. All right, so 1.76 times a height of 9, divide by 2 because it's a triangle, 7.92 is the area there. I've got to do this little triangle. So it has a height of negative 2.73, a base of 0.54. It is a triangle, so divide by 2. And I get negative 0.74. I've been using 2 decimals on everything else, so we'll use 2 here. except I've lost my ability to write. There we go. This other one is a rectangle and triangle combined together. So the rectangle has, oh wow, I think that is 5.37. Write clearer when you're doing these things. Pretty sure that's negative 5.37 times 1.9. So negative 10.20 we'll say. And then the triangle, don't get confused on this one. The height of the triangle is not 15.07. Oh, that's a 2. Let me see something. 15.02 minus. That's this is actually a 3, I think. That's actually a 3. Oh wait. Hmm. 2.73, and it should go down another 2.6, 5.33. Yeah, so that's a 3. So that changes this a little bit. 5.33. You really should write clearer. Times 1.9, 10, negative 10.13. We'll call it. We're going to be off anyway, but might as well at least be close to right. What I was saying is the height of this triangle is not 15.02. It is 15.02 minus 5.33. So the height of the triangle is only 9.69. And then it has a base of 1.9 divided by 2 because it's a triangle. So negative 9.21. So the total area here is, we add both of those together. 9.21 plus 10.13, negative 19.34. Okay, let's go ahead and add our extra little reference line where we have this, where's the bottom? There we go. Where we have that sitting. Okay. All right, now let's draw our shear and bending diagram the best we can. So let's put the reference for it somewhere near the bottom. And we'll say that M equals 0. Our units are kilonewton meters. These are kilonewtons. We start at 0. All right. Now this one does have concentrated moments on it. So we can't forget the very, very first thing we see is M1. So we're at 0. M1 is clockwise, so that's plus 1.7. So we're going to go up 1.7, then we're going to go down 3, up 16, so up to 12. So we need to go up to around 20. So let's see what we need to do to get to 20. Wow, we're going to have to count by 4s maybe. 4, 8, 12, 16, 20. That'll give us close without having to crowd too much stuff. Counting by 3s might have been slightly better, but maybe let's do that. Let's do 3s. Although I like having even numbers there to estimate between. So let's just leave it like this. It doesn't really matter. So we start at 0, 1.7. So right here. Oh, do want that. Right there. 1.7. It is, oh, no. This is a concentrated moment. So it's a step change. So the very first thing that happens is a little jump up to 1.7. Then we have the first negative triangle. So we're at 1.7. We're going to lose, my area is minus 3.26. So I go down to negative 1.56. So here's negative 4. So right in there, we got a bunch of little stuff going on here. Negative 1.56. Technically, this should be a curved line. I'll try to indicate, kind of exaggerate the fact that it's curved. Then we have plus 16.2. So that's the area of this guy. So that's 14.64. So right in here. This is a constant shear, so it's straight from the beginning to the end of this little section. So that means a constant slope here. So this is not a curved line, it's straight. Then I add another 7.92. So at 22.56. This one is curved. I start out kind of steep and I get to 0 right here, 0 slope. So I'm going to end up at a horizontal slope, start out kind of steep, and kind of connect the dots. Then I start having the negative areas. So I'm at 22.56. This is my peak. But let's go ahead and finish it out to see if we got close to the right number. So minus 0.74. So 20, still positive, but 21.82. Little curve in there. This one is curved because there's a triangle in there. But it's maybe not as curved because it doesn't go to 0, so it doesn't actually get a 0 horizontal slope anywhere. It's sitting underneath this rectangle, which kind of mutes the severity of the curve. Oh, shoot. Somebody in the chat mentioned this, and I totally forgot it. Or it made me remember what I forgot. So let's erase a couple of things. So the question actually is... when you have moments, bending moments that are applied to the beam, not the internal ones, but M1 and M2 in our picture, which we forgot M2 is what we forgot to do. Do they go up or down when they're clockwise or positive? So what we agreed upon, and this is part of this agreement. So these sign conventions here and here control this. So what we are agreeing on is that clockwise external moments are positive in the shear and bending diagram. Counterclockwise, like we have here for M2, that was kind of why I was getting a little bit worried here. M2 should have taken our step change straight down. So let's go back to this point. So 14.64. And I forgot to include this concentrated moment. It's counterclockwise, so it's going to be a minus. So 14.64 minus, its value is 2.5, 12.14. So right there, so straight down, we'll put it 12.14 right there. Now we add, so plus 7.92 from the triangular shape, still positive area. That gets us to 20. So I knew I was off a little bit, but I wasn't sure why. Now I know. We'll kind of curve that to show that that one is not a straight line. It does get to horizontal. Then we have minus 0.74. So that gets us to 19.32, little curve. Then we have the 19.34. We're at 19.32. That gets us to 0.02 or negative 0.02, which is really close to 0. So that's a good deal. This one doesn't start or end at our horizontal or vertical, so we just kind of have to, do something like that to show that it's curved. So our peak is right there. M max is equal to 20.06 kilonewton meters at, let's see, 1.5 plus 1.8 plus 1.76. 5.06 meters from left end. So that's the where we would find the maximum bending moment. So here's the little, can't even color in that small with this marker. Well, fake marker. So there's our bending moment diagram to go with the shear diagram. So again, we didn't spend a whole lot of extra time. I did explain every little step, so you could have done it slightly faster, but they do take a little bit of time to do. What you gain is the entire picture of the beam. In fact, in a way, if you were to take this bending moment diagram and invert it, so turn it upside down, so like this. So if you kind of did something like, well, instead of curving this way, it does something like, well, it's more than that though. Something like that. That's the exaggerated shape of the beam when it deflects. We'll get into actual beam deflection later. But the bending, remember, most of the bending moment, this is how the beam bends. And so we can use that to sort of get an idea of what the beam looks like. And positive bending moments, like we have all through most of the diagram, is positive. There's this tiny little section that's negative right here. Positive moments, remember, positive is the beam bending this way. So there's tension on the bottom, compression on the top. The negative moment is the opposite, and it's right here. That's the only place where it's negative. And that's because if we look at our picture, our beam is got this, first of all, it's got a concentrated moment that's trying to pull it back up, but right here it's kind of hinged on this pin, and so there's one little section where it's doing this weird, it's being pulled up, but it's also wanting to deflect with tension on the top of the beam, so it's got a weird thing, and that's what their bending moment is showing us. Their bending moment diagram is showing us that weirdness, where we actually have tension on top and compression on bottom. Well, not there. Actually, there we have tension and compression, but right in this little spot where the beam is supported on the roller, there's tension on top of the beam, which it doesn't want to write now. Well, fine, you get the idea. Right in just that one little section, it flips because of it being supported and the way it's loaded with this concentrated bending moment on the end of it. All right. So we will do more of these, not today, but we'll do more of these, get practice. I did open up homework set 13, which has more of these in there. Like I say, they're tough to put into WebWork because you can't draw in WebWork, so you have to draw in words, which is a little bit cumbersome to do, but it does let you do them. And then we've got, where are we at? July 8th. Moments of inertia. Oh, no. I said we were going to do some more shear and bending moment diagrams, and we'll start moments of inertia. And lab 1. So lab 1, normally, if we were on campus, as a regular part of the school year, we would go in the lab and actually do some testing with a tensile test machine, but y'all are scattered all over everywhere, and that's not what we're going to do. So we're going to do a SolidWorks version of that lab. So if you don't have SolidWorks, try to get it installed. You can ask the help desk. Even if you don't have to go in person. You can email the help desk and get access to SolidWorks. So you can download it and get it running. So we will need that. If you just can't get SolidWorks running, you can do similar things in like Fusion 360, which is free to use. It's just a different version of CAD modeling. All right, we will be back actually tomorrow on Thursday, and start this lab. It's gonna stay. You have like 2 weeks or a week. I don't remember exactly. You have a lengthy amount of time to finish lab 1. You don't have to get it done tomorrow. But we'll do some more shear and bending diagrams and talk about this idea of moments of inertia. See you tomorrow. Man, it got hot out here.